joule there.
He's got 79.7.
79.7. And then the latent heat of vaporization for water, 597.3 calories per gram, or 2,500,000 joules per kilogram. So as we're about to launch into our problem, we need to figure out what we want to deal with, joules or calories. Do you care?
Let's use calories.
All right. So if I have 50 grams of ice at 10 degrees Celsius, sorry, what planet is that on? Negative 10 degrees Celsius. How much energy will it take to make 50 grams of steam at 105 degrees Celsius? And the way to approach this problem is to do it step by step. First, we need to get ice up to the melting point, then we're going to melt it, then we take it up to the boiling point, we'll boil it, and then we'll take it up to the final temperature. Because everyone loves a graph. So temperatures in degrees Celsius, and then the amount of energy. So we're going to start out at negative 10. We're going to go until we get up to 0. We're going to melt it, so there's no change in temperature as we're melting it. Then we're going to take it up to boiling point. We're going to vaporize it, and then we're going to take it up to the final temperature. So we have we have 5 different segments here that we need to do, and then we're going to add them together. We need to know the latent heat of fusion, the latent heat in vaporization, which are already written on the board in calories per gram, and we need to know the specific heat, in other words, the indication of the amount of energy it takes to change a certain amount of mass of H2O to a new temperature. And so this one, we know the specific heat of liquid water. So I'm going to write H2O liquid. That's 1 calorie per gram degrees Celsius. Specific heat of ice. .05 calories per gram degrees Celsius. Make sure I saw that correctly. Oh, that's joules. Dang it. All right. I need to get it to the right units. 0.05 divided by 4.24. So 0.490 calories per gram degree Celsius, and specific heat of water vapor, or we'll just call it steam, since that's what it is in this case. .501 calories per gram degrees Celsius. All right. All right, so step by step. questions before we plunge into the math? All right, so we're gonna do ice from negative 10 degrees Celsius to 0 degrees Celsius. Because this is dealing with a change in temperature, we're using the Q equals MC delta T. So the amount of energy would be the mass, which is 50, times the specific heat of ice, 0.490, times the change in temperature, which will be 10 degrees Celsius. Because I'm going from negative 10 to 0.
Really quick. Why are you going negative 10 to 0?
Because that's where the problem starts. I start out with ice at negative 10 degrees Celsius, and I'm trying to get up to there. I can't take ice all the way. Ice will melt at some point.
I see.
And so we're taking it up to the melting point.
So we're multiplying 50 times 0.490 times 10,
Yes,
and we got 24.5,
24,
0.5,
24, 25,
0.5.
0.5. All right, units?
We are going to call those calories.
As you should. Yes,
I was
calories.
gonna keep trying to go with the rest of it at the bottom.
No, but the grams canceled out with these grams, and the degrees Celsius canceled out with those. All we're left with is calories.
Okay.
So now we have to melt it. We melt the ice. No temperature change. So the amount of, so Q is gonna be equal to the mass times the specific heat of fusion, since that's the one that deals with that process. Technically, we're doing the reverse of fusion, but it's the same number, whichever way you're going, just other than one's positive, one's negative. But I have to put energy in order to melt it, so it's gonna be positive.
So it's gonna be positive 24?
So that'll be 50 times the, here we go, times 79.7.
Oh,
That's 50 grams, and that's calories per gram. So the first one was 242.5 calories. So how much energy did it take to melt it?
I got 39.85.
Units?
I just keep going for it.
So it takes considerable more energy to melt it than it does to just get it up to 0, to change it 10 degrees. From a weight loss point of view, if I have ice in my mouth, it will melt. The energy that goes into melting it is coming from me. So the amount of energy that I have to lose energy in order to melt the ice. And if I'm losing energy, that energy is coming from somewhere. And then pick the units you want.
And so that top one isn't 242.5. No, it's just 24.5.
Oh,
Yeah, for multiplying the 50 times the 4.90 times the 10, we get 24.5.
something's off there, because 50 times 10 is 500
Okay.
times something a little less than half, so 242.5 actually makes sense.
Okay, hold on.
Is 242.5, maybe, it's gonna be somewhere, it's gonna be somewhere around there.
I got 245.
You have 245?
Yeah.
Okay.
Yeah, okay.
All right. We now, at this point, we've pumped in a little over 4,000 calories. We now have a pool of water at 0 degrees Celsius. We now need to get it up to 100 degrees. So we're now on this stretch of the phase. So we're taking liquid water, H2O liquid, from 0 degrees Celsius up to 100 degrees Celsius. We're dealing with a temperature change, so which formula are we using?
MC delta T.
Yep. So I still have 50 grams. My specific heat is convenient 1 calorie per gram degree Celsius, and the temperature change,
100.
yep. So, I can do that math, that's 5,000. I'll write it out here. It's 5,000 calories. So 50 times 1 times 100. So far, the biggest change, the biggest amount of energy we've had to spend is getting the water, raising the temperature of the water 100 degrees Celsius. But now we have to turn it into gas. We're gonna boil it. And so now we're dealing with a phase change. So boil water. We're now dealing with the heat of vaporization, which is erased, or I wrote. Oh, no, right here. That number right there. So we're dealing with MC sub V. So I have 50 grams times 597.3 calories per gram.
That's 2986.5.
29865
Yeah.
units.
Calories.
And so we get the biggest expenditure of energy right there. We now need almost 30,000 calories. And the last bit is we need to get steam up those last 5 degrees. Steam from 100 degrees Celsius to 5 degrees Celsius, 105. And we're back to MC delta T.
And so the last one we just did, we just turned that into gas, or you said that was fusion?
What, here?
Yeah.
When we melted it, we used the latent heat of fusion.
Now this last one right here, we got the 59?
Oh, latent heat of vaporization.
Okay, that was the boiling. Okay.
Yeah, we're taking liquid into gas, latent heat of vaporization.
Okay.
And what's the CV we use?
What does CV mean?
You don't know what we use, which one are we just using now? Like the same thing? Are we using the same thing for in the last one?
Oh, for the last one?
Yeah.
No.
Or,
CV is the latent heat of vaporization. We're using this number right here for the last C. That's 501 times the temperature change, which is just 5 at this one. So 126.
Sorry.
125.25 is what I got.
125.25. So it doesn't take a whole lot of energy at the very end. But it's only because we're taking it up only 5 degrees. We're not taking it very far.
I have a question.
Yes,
Okay, so the original question was 50 grams of ice at 10 degrees Celsius. And then how much would it take to get it to 50 grams of steam at 105 degrees Celsius?
Yes.
Correct? Okay. So,
but one correction, I don't know if you have it written down, but -10.
oh, yes.
Okay,
Okay, so in order to get the answer, we had to do ice, water, and then finally steam. We couldn't just do the last part, the steam part.
because we're starting from here, you add all 5 of them up. Because it takes energy to get the temperature changed, and it takes energy to change the phases.
Okay, so we're not at the final answer yet.
Right.
Okay, sorry.
But the final answer is just this one sum away. We know how much energy it takes for each part, we now add them all up.
Okay.
Hopefully this is right, mister. I don't know how to get my numbers right, but I got 39220.25.
Anyone else get the same number?
I'm at 9,355.
I got 12,341.
Well, I know it has to be more than 29,865.
Or it has to be more than 100.
I thought that's a, oh, never mind.
You're adding that, plus that, plus that, plus that, plus that.
245 for life,
It looks like about 12,000.
5
It's 3,
for life,
3,
5,000
5, it's 11.
for life.
So, are you confusing that dash with a decimal there?
Oh, I thought that was a decimal.
So 39,000?
Yeah, so.
Yeah, that's what I got.
39,220?
Mhm.
All right,
That's what I had.
yep, you're right. And let's finish it off.
Calories.
Yep. That is the amount of energy it takes to take temperatures.
Is this gonna teach us how to cook or anything like that?
Say that again?
Is this gonna teach us how to cook?
No. I mean, you could actually, if you're boiling water, you have water starting out at whatever tap temperature is, just 20 degrees Celsius, why not? You're taking it up to boiling, so it takes a certain amount of energy to get that. Then the actual boil it, that takes energy too, to boil it. All that energy you're paying for. I mean, you can take that number of joules and convert that into kilowatt hours, which is a different unit of energy, and you can figure out how much it costs you to cook. It won't help you cook, but it will make you more aware of what it's costing you to cook. Which is probably still less than getting it from a restaurant, but.
Alright.
Not done yet. We haven't gotten to the depressing part, we got 5 minutes.
You could depress us.
What are we, okay.
Well, come on then, mister. Show us what you
What's the
got.
depressing part?
4 laws of thermodynamics.
Everything will die.
We'll get there.
I was gonna say, now, that's depressing.
The first law is the zeroth law,
Zero it?
because they came up with the first law and the second law, and then someone realized, oh, wait a second, there's something more fundamental. And so instead of renumbering them, they just made it 0.
Okay.
Now, the zeroth law is what I consider to be common sense. However, the application is not necessarily.
Why would you start with the Zeroth Law? Why don't you start with 0?
They started with 1, and then later on added this, and they felt it belonged before this one, and they didn't want to renumber.
0 pit.
If I have a thermometer here, encased in glass, and I'm picturing a mercury thermometer just because that's the way I was raised, or whatever they use nowadays. So let's say I have a thermometer here, and there's measuring a temperature, and we'll just say 70 degrees Fahrenheit. What does a thermometer actually measure?
Heat.
It measures the temperature. Temperature of what?
Surrounding air?
Not the room. What'd you say?
Surrounding air? Or I don't know.
Depends what you mean.
Environment.
Pardon?
Environment.
No,
The
actually
stuff
no.
in the thermometer,
Pardon?
the thermometer,
More specifically,
the stuff that's like inside it.
yeah. If it's a mercury thermometer, it's actually an indication of the temperature of the mercury.
So the temperature of the room gives off the temperature of the mercury?
All right, so here's the zeroth law. It basically says that if it's in thermal equilibrium, which means the temperature's not changing, that if this is in thermal equilibrium, it is the same temperature as the glass that surrounds it. If the glass is in thermal equilibrium, it's the same temperature as the air around it.
Mm.
So therefore, this would be the same temperature as the air around it.
How does it so happen that, how does the mercury expand, or?
Yeah, exactly.
How did they figure out that it just so happens to expand to the right, like, or is there like?
There's actually some principles behind it. The ideal gas law fits, even though it's a liquid, that the volume, if the pressure stays the same, the volume is directly proportional to the temperature. It can be derived also, but. All right, so the zeroth law is sort of, if A is the same temperature, it's in thermal equilibrium with B, and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. It's basically the transitive property. If A equals B and B equals C, then A equals C.